Hey guys, welcome back. Today we're going to finish up this chapter. I know, in 2 days. I'll try to make it go a little bit quicker as well. There's really just one new topic that we need to go through. Sorry, yesterday's video was a little on the long side. So we are, again, just kind of talking about penguins. So the heart rate for the penguins in response to how long they can dive. So if they start out with a higher dive heart rate, then they're going to be burning through oxygen quicker in their bloodstream, and they will have to resurface sooner. So they researchers looked at these penguins, and I guess they fitted them with heart rate monitors, or the same penguin with the same heart rate monitor, and they found that penguins with larger heart rates had a shorter dive duration. So the faster the heart rate, the slower, or the shorter the dive rate. So the longer their dive was, the slower their heart rate had to be. Again, the whole point from this was that even though this looks like it's linear, always graph the scatter plot and the residual plot. But the residual plot can make it a little bit easier to notice that we've got some gaps here showing that we have overall curve data, which needs to be re-expressed. We talked about how yesterday we could re-express this by squaring it. And then we would have a re-expressed model that looks something along the lines of this. So the dive heart rate squared, and then it's going to have some new slope as well. All right, so the other thing that we talked about is the further that we deviate from the mean for the explanatory variable, the less we should trust the prediction. So even though the model might be just fine further out, in general, we shouldn't trust it as much the further we get away from the mean point. The other thing that we learned is that if you must extrapolate, then at the very least, don't expect it to come true. We were given an example with oil prices, and 3 times they extrapolated, and all 3 of those models were not correct. So it didn't stop them from getting paid lots of money to make those models, and people still try to predict what's going to happen in trends in the future. But overall, we know all of that's pretty unreliable. The only thing we can actually do, I'll go back to that, is interpolate. So we can fill in missing data points, like trying to figure out an estimate for the class size of 1969 from that small local college or whatever. That would be okay because we're interpolating missing data that was within a domain or a set of data or range of data that we had. So that would have been fine. But extrapolating, we don't know what's going to happen with trends in the future. We talked about large residuals. So here we had a large residual. If we graph this out, this is clearly an outlier. You can see how it changes the slope of it as well, and it actually kind of makes the slope of the model go away from the point. So if we remove this one point here, and of course we would be upfront about what we're doing, we would get a better model. So that's what we would want to do, because the whole point is we want to get a better model that has a smaller standard deviation for our residuals, or standard deviation for the error. Almost said standard error, but that's something completely different, related but different. Anyway, so we want to give a model that has a higher predictive accuracy, which is measured by the standard deviation of the residuals. All right. Also, high leverage points are points that are far away from the x bar, from the mean value for the explanatory variable. I guess I should have shown those there. They're called high leverage points because they have a lot of leverage on changing the slope. So if we had a high value for bozo, that would give us a high correlation coefficient and a positive slope. If bozo was a bozo, which is kind of funny, then it would make it negative, just at one point there. So it's a high leverage point. Both of these would be considered influential as well. If he was like kind of in the middle here, or on the y bar. So if you had like a y bar here, that wouldn't actually change the slope, but it would. It wouldn't change the slope, so it would have high leverage, but it wouldn't be influential, because if we remove that point, it wouldn't change the slope. So that's the difference between those two. So influence is that if we remove the point, it greatly changes the slope. So here we have our normal slope that we would expect, and this is our mean point. So these are the positive ones. These are the positive correlation, products. Some of the products of the z-scores will give us a positive correlation. The ones that are on the mean lines for x bar or y bar, those aren't going to change the slope because they're going to have a 0 product. These two values and these two values here would actually lessen the strength of the correlation. So overall we had 0.7. They weren't all in a line, but there weren't as many that counteracted with negative z-scores as well. Now what happens if we add this point here? Well, that point's it's actually going to change the mean point, and it's going to pull the mean to the right and then slightly down. If you notice here, but mainly pulling it to the right. So now notice what happened. All these points here are still going to be positive products of z-scores. There's not very many over here, but these negative ones are going to counteract these as well. So what's going to end up happening is we're going to have a smaller correlation coefficient because of that value. And if we look at the slope as well, because of that, our slope is not going to be as strong either. So we're not going to be able to deviate as many as we do with the x and the y. Okay, so that would change our correlation coefficient, and of course would change the slope as well. So if removing the point would change the slope greatly, then we would say that point had influence. Now, if it was in line with it, like this one over here, that obviously has high leverage, it would not be influential, because if we remove that point, it wouldn't change the slope very much. All right, if we look at this point over here, again, that was like our high outlier. It actually counteracted if we changed, this is easier to look at. So the positive and negative here, if we put a big negative over here, that's going to lower the slope and lower the strength of the correlation coefficient. So we got an issue with the outliers. This one here totally changed the slope, because now all these points are all going to become negative as well. I guess I could actually probably show that real quick. So let me graph. So before the point, we would have kind of a mean, something about right there. And after we add this point, now our mean is going to change, and it's going to be drawn lower here. So now the averages are going to be lower because of this outlier. So notice all these points now are negative, along with this one's also negative, so our slope became negative. But before, we would have, in general, positive slope. Not very strong, but a positive slope. So notice how that one point, drawing it down here, now all these points and this point are negative, and so it changed the slope. So that one would be considered to have a lot of influence, and of course it had a lot of leverage because it was so far from the x mean. And this one had leverage but not influence. The other thing we'll remind you is correlation is not causation. They keep bringing it up. I'm just going to keep reminding you of it. So we can say with the associations in general, this is actually kind of funny. So the number of TVs per person in a nation and the life expectancy. So as we have more TV and more Netflix, I almost said a different thing with Netflix, but I am smarter and wiser now. So as we have more free time and we watch Netflix together, so dodging it. Anyway, then the life expectancy goes up as well. So does that mean that Netflix makes us live longer? No, there's clearly lurking variables. So wealthier nations that have better health care, they also are going to have more TVs per person, right? You can see the same thing here. So the number of doctors that you have, that increases life expectancy. It's clearly doctors have an impact on life expectancy, but what we're really saying is that wealthier nations that have better health care, have more access to doctors, are going to have more doctors per person, and then you're going to have a higher life expectancies in those nations as well. So is it the TVs, or is it the doctors, or is it really wealth that we're measuring? Probably really wealth. So there's lurking variables. We can say in general there's a positive association between the number of TVs per person and the life expectancy. Notice I didn't say that TVs cause higher life expectancies. So very careful in the language. In general, we can say that nations that have more doctors per person also have a higher life expectancy. That's fine. We can describe the association that we're observing in nature, but without a carefully designed experiment, we cannot prove that it was the doctors or the TV. Is it Netflix or healthcare that's increasing life expectancy? All right, the other example, of course, correlation is not causation, which we talked about, Oldenburg, Germany. All right, the other thing I want to point out, and this is really the only new thing, is working with summary variables. So here we have height and weight. Now, if for every category of height, if we took the average weight for those people, we would end up with a graph like this. And so let me kind of show you how these two are exactly the same thing. So there was only one really, really tall person here, and so the average was the same with this one and this one. But notice for these people who were 73 inches or whatever, there were two of them. If we took the average, see, I took the average of those two, the average would be collapsing. So the average is always going to collapse towards, the middle, the average, right? Same thing here. This group, the average would be here. This group, which had a bunch of spread, now is only being represented by this one variable. So if we work with summary statistics and we graph out the averages for each height, breaking them in categories, we're going to remove a ton of variation that we would have in all the points if we graphed it out over here. So notice this looks like it has much more a much higher predictive value or predictive accuracy because of standard deviation of the the errors or the residuals is going to be a lot lower than the actual data themselves, because we're dealing with summary variables like the average mean weights instead of the actual weights themselves. So we're artificially removing a lot of variation in the response variable by working with means, but do be very careful. Just this, sorry, jokes. They are exactly the same. They're going to have exactly the same slope if you work with the summary statistics. But the problem is that we're not actually showing the actual amount of spread that we have in the variation. And so be careful when you're working with summary variables, and they'll always have a stronger correlation and a higher R squared, naturally. And the best way to measure the strength of the association, of course, is the standard deviation of the residuals, which will tell us the average predictive error that the actual values were from our model. All right, so go ahead and get out your calculator. This is a really fun exercise that we're going to do. So we're going to graph these 4 points, and then we're going to add a 5th point, which is going to be all these different points here, and we're going to see how that 5th point changes the correlation, the slope of the regression line, and the size of the residual. Okay, so this is going to be pretty fun. So go ahead and get out your calculator. This is really good kind of hands-on learning. So I'm going to go ahead and clear out my list. So to do that, I'll go to second, memory, clear all lists with the 4th option, hit enter, and then stat, edit again. And in the X list, I'm going to put 1, 2, 4, 5, and then just make sure your Y list is in the same order. So 1 went with 2, 2 went with 6, 4 went with 2, and then 5 went with the 6. Okay, so then we'll go ahead and graph the scatter plot. Just make sure we have that going. So scatter plot on list 1 to list 2. I guess I'm using blue. Actually, I want to use blue. Blue's fine. All right, then hit zoom 9, and you should just be graphing out these. And if you want the window to be the same, you can go into window, and the X-min is going to be, I think I did -2. Oops. So that's going to be -2. And then the X max, I think I did 11. The X scale was by ones. It is by ones, yeah. The Y minimum, I think I did -2 again. And then the Y max was 11, and the Y scale was Y again. Okay, then just hit graph. Don't hit zoom stat again, because you'll just undo what you just did. And now your graph should look exactly like mine. So kind of cool. All right, so there's our 4 points there. If we graph, if we run, so I'm going to go to stat, calculate linear regression, so that we can get our model, right? And go ahead and store the regression equation as Y1, and that way it'll automatically graph it for us when we do this. And the whole process is going to be sped up pretty quick. So once we do this one time, we're pretty much done. All right, then hit calculate. That'll give you those values. Those are already filled in the table, so not really that big of a deal. So our correlation is 0.316. Slope of the regression line, that's going to be the 0.4. That's the A value there, right? And the size of residual, there is no residual on this one. All right, so we got that going, and then if you hit graph, it'll give you the slope there. All right, so now what we want to do is add an additional line. The next point we're going to add is this 0.34. So spoilers, 3.4. So there it is. And notice at this 0.34, that is the mean point for these points, by the way, in case you're curious. And so it's going to be on the line, right, on the regression line. So is that going to change anything? Think about it. I mean, honestly, think about it. It's kind of cool. So what it is going to change, because now we have one more point. It's not going to have a positive or a negative z-score, because it's going to have some of the products of z-scores of 0, 0, right? So, but it is actually going to lower our correlation a little bit, because now we're dividing by n minus our sample size went to 5 instead of 4. So we're going to be dividing by n minus 1, which is 4, instead of n minus 1, which used to be 3. So it should actually lower our correlation. Our slope, I believe, is going to be should be slightly lower as well. And the 5th point did not have a residual. So we're going to graph this out, put it in there, and see what we get. So go into stat, edit, and add the 5th point, which is the mean point of 3 and 4. Oops. 3 and then over to 4. What's nice is I'm actually filming this at a decent time. It is only 10 o'clock at night right now. But it also means my neighbors are probably trying to go to bed. So, sorry. All right, and if we hit, just hit graph again. And notice that it's on that point, but that regression line has not been updated. So what we need to do is quit out of that. So second quit, and then arrow up to run your linear regression again. Our lists are still the same, and it's just going to store it again as y1. So just hit enter. Okay, so interesting enough, the correlation stayed the same, like I said it would, but it did not change the slope. And I'm wondering why it didn't change the slope. Oh no, I'd have to think about that, and I guess you do too. All right, so basically it was the same. We didn't have any change in the slope. Okay, so next point we're going to add is the 0.86. So the 0.86, which is going to be right here. So it's going to be further out. It's still on the line, so it shouldn't change the slope, I suppose, but it will change the correlation coefficient, and the correlation coefficient should be stronger now because it's well, no, if it's on the line. No? Yeah, it would be positive, so it should be stronger. Slope of the regression line should stay the same, I'm guessing. So let's go ahead and add that point instead. So we're going to go to Stat, Edit, change the point to 8, and the other point over here is 6. Okay, and then you can hit Graph. You're going to have the new point here. It is still on the old line. Quit out of that, so second mode to quit. Run your linear regression. And we do have the same slope. Our correlation did go up to 0.5 now. So there you go. Kind of cool. But the slope stayed the same. Interesting. So hopefully you're starting to pick this up. The size of the residual is still 0. So no big deal. All right, let's try another point, which is 10, 7. So 10 and 7, I think, is that point right there. So yes, it is right there. It's really, really close. It looks like it did change the slope altogether because it wasn't quite on the other one. And let's do it. I'm just going to cheat. All right, so our correlation went up even more, of course, because it's a stronger, higher z-scores. Some of the products of z-scores. Looks like the slope of the regression did go down a little bit, which is interesting. And then, yeah, we're good. And we have a slight residual there. Okay, let's look at the next one here, which is going to be 3, 8, which is this point here. All right, so this is one of our outliers with a large residual. So what is that going to do? Well, it is on the mean point, if you notice. So it's not going to change the correlation from the original one. It should have the same correlation, but it is going to move our mean higher. And so the mean point is going to be higher now. And so our entire y-intercept should be higher. And in fact, it is higher. Yeah, it is higher because I didn't line up the axes. So all it did was move it up, which is really cool, and didn't change the correlation. Apparently it lowered the correlation. The slope is the same, but it moved it up, and it did have a residual. So why did it change the correlation? Because it should be on the mean point. Is this whole we're divided by an additional number, but if that did it, then so should this number have done it as well. Curious. All right. Anyway, moving on. 1 and 7. Okay, so 1 and 7. That is going to be a negative value, so it is going to decrease the slope. Of course, it is going to wreck the positive correlation that we had going on before. So it's going to now have a negative slope. Our positive correlation apparently now is next to 0, and we did have this residual going on there. So that's kind of cool. And then 8 and 9. Okay, so that's going to increase the slope, increase the correlation drastically as well. And we did have a slight positive residual. Okay, and then the last one I'm going to show you is 10 and 0. So 10 and 0. All right, so that is going to move our mean point down, it looks like. Going to make the slope negative all of a sudden, and our correlation will probably be next to 0 as well. Okay, it was actually even stronger because it was so far off to the right. I guess that does make sense. Okay, cool. So hopefully that made sense. Some of that stuff, still have to wrap my brain around it, but kind of cool stuff. I'm just working through that, and good stuff. All right, so let's go ahead and go through the problems here. Number 24, we'll do the even problems. College admission officer defending the college use of the SAT scores in the admission process produced the graph below. It shows the mean GPAs for students of last year's freshmen. All right, so notice the mean GPAs, again, we're using summary statistics just like we did here. Okay, so we artificially removed a bunch of variation in all the individual students by only expressing those based on the X values, based on the mean for the Y values. So do be careful with this. We're going to get the same regression line, except it's not going to tell us exactly how good of a predictor the model is, because we artificially removed a bunch of the variation, the residuals. Okay. All right. No big deal. Okay, why should we want to look at the scatter plot for each individual student's GPA instead of the mean GPA? So we want to see all the variation. I mean, this could be like total random spread all over the place, and then just whenever they collapse them to their means, now it looks nice and neat and clean. Okay, so we do want to see the actual variation we had in the beginning. All right, because when we're dealing with summary values, we're removing variation. So it gives us more confidence than we probably should have. Do higher SAT scores cause freshmen to have higher GPAs? What could possibly lurk in variable? Just academic performance. So a stronger academic student is probably going to score higher on the ACT and probably going to have a better GPA in college. That just kind of makes sense. So was it the ACT, the SAT scores that cause higher GPA? Not necessarily. But we do use SATs for entrances into college to make sure that you can actually do the coursework, and so we don't have as much dropout rates. And I think if you looked at dropout rates for lower SAT scores, they probably have higher dropout rates than for students that went to college with a higher SAT score. Again, lurking variable is we're just using the SAT score as a measurement of academic performance or capacity or potential or whatever, instead of just the SAT itself causing higher GPA scores. All right, 28. The graph below shows the ages of men and women at first marriage. This came from the census, which is kind of cool. Clearly, the pattern for men is similar for the pattern for women, but the two lines are they getting closer. So it looks like people used to actually get married older, and then in the 1950s or whatever, they started getting married younger when they came back from war, I guess. I don't know, the boomers. Okay, cool. And then now people are getting married later and later, which means I'm normal. Guys, I'm normal. I'm not normal. You didn't believe that for a second. Okay, but what's actually really interesting is we compare this data. And again, these are averages. So this is the average age of people from the first marriage. So there's definitely much more variation. You could have older couples in general than younger couples. But what is cool is looking at the difference between these two ages. So if we subtract, so we'll do men minus women because we'll do the bigger one first. So we have positive values. These are the differences between the ages. So men minus women's average age for that year. Also notice we had more data they were collecting every year from the census, I suppose, but they used to only do the census not as often, or they just didn't put the data there. I'm not sure. But anyway, it's kind of cool seeing how that graphs out. And then the difference, so as the years went on, we noticed the difference, even though the ages were rising and falling here, the differences have always been narrowing, or it looks like in general have been narrowing, which is really, really cool. All right, so then we looked at the residuals here. It doesn't necessarily look like we have much of a pattern. It does kind of look like it's kind of going up and down and up and down, but there's no way to actually straighten that out when you have sinusoidal behavior like that. So there's nothing we can really do. It's not like we just square it or take the logarithm to fix it. So it's good enough. We're gonna roll with it. What's the correlation coefficient? So looking at the analysis here, I don't know why there's a gap between DIF and the differences. So it's the age difference is the dependent variable. That's what we're interested in. The R squared is given here. The S, remember, is the standard deviation of the errors, of the error or the residuals. And the constant is going to be our y-intercept. The year is going to be our slope. Okay, and that's also telling us what our explanatory variable is as years go on, right? And this is actually not years from 1880 or anything like that. This is actually year from year zero. So BC, right? I don't even know what we call that. Year zero. Anyway, moving on. All right, so interpret the slope. Oh, to find the correlation, we just take the square root of the R squared. That's how we get the R. But remember, it's plus or minus. So you'll always get the plus, but this is actually negative because when we looked at the scatter plot, it is negative. So look at the scatter plot to get the context, and it is decreasing. All right, interpret the slope of the line. So our slope is going to be this negative 0.016565. So that says on average, our model predicts that for every year, each year, there's a decrease in the age difference by 0.0166. If you want to round it, it's fine. All right, so pretty cool. So that's how much it's decreasing on average from our model tends to show each year that we go on. All right, predict the average age difference in 2015. So I'm going to get my calculator again and clear out of that. I think I've already put this in the calculator. So because I'm lazy, I'm just going to go up to it. All right, so here's my slope times the year 2015. So it's not years since 1880 or anything like that. It's just 2015 plus our y-intercept. So that means back in year 0, the average age difference we would have expected was 35 years. And people even lived at 35. That's kind of disturbing. So again, we wouldn't, it's funny to interpret the y-intercept, and often it makes no sense at all. And it's almost always going to be extrapolated. Almost always, not always, just depends on your domain. But anyway, 35-year age difference between men and women, that's ridiculous. But anyway, it makes the model work, so don't worry about it. So the predicted age difference that we're going to expect is going to be 1.68, which if we look, let me go back here, 1.67687, yeah, so that's going to be about right here. So it looks like our model is going to go to about that point, which looks about right. So we know we did it right. All right, describe why you might not place much faith in that prediction. Well, because it is extrapolation. Last year that data was collected looked like 2005 or something like that. So it is extrapolating. We don't know. Maybe the gap and the difference between the ages of couples at first marriage or whatever, maybe that started to widen again. I don't know. Nobody knows. Well, we could look and figure it out because 2015 already happened, but I don't know. All right, see you guys. Have a good one. I guess it's a slightly shorter video. My bad, guys.